Last lecture, we gave an introduction to the course, and now we'll actually get started with the contents. We'll review history of computer vision over the last few decades, just to give a perspective of where the field started from and how it has evolved over the last few decades. So this lecture is structured into four parts. We'll briefly describe very initial forays in the field in the 50s, 60s, and 70s. Then we'll talk about efforts that contributed to low-level understanding of images in the 80s largely. Then we'll go on to high-level understanding that the community took up in the 90s and 2000s. And of course, we'll then cover a brief history of deep learning in the last decade or so. To start with, a disclaimer, this is going to be a history of the field as captured from multiple sources, Selesky's book, as well as many other sources that are mentioned on each of the slides. It may be a slightly biased history from multiple perspectives. One, perhaps the way I have seen it and I have seen it to be important. Please bear with that personal bias. It may also be biased to the topics that we cover in this course, may not cover physics-based vision, geometry-based vision in too much detail. Once again, I'll refer you to those books that we talked about in the previous lecture if you want to know them in more detail. There's also a slight predisposition to work down on images more than videos, but still hopefully these slides give you a perspective of the field and how it's evolved over the last few decades. The earliest history of computer vision was way back in the 50s when two researchers, David Hubel and Torsten Wiesel, published their work called Receptive Fields of Single Neurons in the cat's striate cortex. So they conducted multiple experiments to understand how the mammalian visual cortex functions. And they took a cat and they did many experiments in this regard, but they inserted electrodes into a sedated cat and then tried to see how the cat's neurons fire with respect to visual stimuli presented to the cat. Incidentally, for quite a long time, they could not make headway, and accidentally, they found that a cat's neuron fired when they switched slides in the projector in front of the cat. They were initially perplexed, but they later realized, and that was one of their propositions, that the edges created on the screen by the slide that was inserted into the projector was what fired a neuron in the cat. One of the outcomes of their early experiments was that simple and complex neuron exist in the mammalian visual cortex, and that visual processing starts with simple structures such as oriented edges. So Hubel and Wiesel, in fact, did many more experiments over the next 2 decades, and they actually won the Nobel Prize in 1981 for their work in understanding the mammalian visual cortex. So this was one of the earliest efforts in computer vision. In the same year, in 1959, there was actually another major development too, which was by Russell Kirsch and his colleagues, where for the first time they represented an image as a set of ones and zeros. So representing an image as a number grid was a huge achievement, which is something that we inherit to until today. And in fact, the first image taken was of Russell's infant son, which was a 5 centimeter by 5 centimeter photo about a 176 cross 176 array that was captured at that particular time. This is considered such a big achievement in the field of vision that this particular photo is still preserved in the Portland Art Museum in the USA. Then in 1963, there was a significant development by a person called Lawrence Roberts, and he wrote a PhD thesis on machine perception of three-dimensional solids. The PhD thesis, in fact, is hyperlinked on this particular slide, so please take a look at it if you're interested. But I think this thesis had some ideas even beyond its times at that point. So the thesis discussed by Roberts talked about discussed extracting 3D information about solid objects from 2D photographs of line drawings. So if you recall what we spoke in the previous lecture, we said that the aim of computer vision is to understand the 3D world around us from the 2D images that we get or the 2D videos that we get, To some extent, this is what was talked about way back in that PhD thesis in the early 60s. So the thesis discussed issues such as camera transformations, perspective effects, rules and assumptions of depth perception, so on and so forth. Interestingly, Lawrence Roberts moved on from this topic, and he's actually more famous for some other big development that all of us owe him for. So I'm going to leave that as a trivia quiz for you to find out. We'll talk about that in the next class, but try to find out what Lawrence Roberts is known for. And the hint is it's not for anything in computer vision, but it's a huge technological development that all of us today owe him for. Okay, take a look at it and try to find it out before the next lecture. Subsequently, in 1966, one of the earliest efforts in trying to uh, come up with systems for computer vision, which happened in MIT in 1966 by Papert and Sussman, who decided that they could use a bunch of their summer interns to develop an end-to-end system for computer vision. They thought they could take a few summer interns and develop a platform to automatically segment foreground and background and extract non-overlapping objects from real-world images. And this is something that they thought they could achieve within a summer. Okay, so this was actually the note that was written by Papert at that time. Obviously, you and I know now that the project did not succeed, but rather the project opened up researchers to the fact that this was a very deep problem and it was not something that could be solved in 2 to 3 months. And we still know that this problem, certain aspects of it are solved, but many other aspects still remain unsolved. Then the years went on, and in early 1970s, there were also works where people tried to study uh, how lines could be labeled in an image as, say, convex, concave, or occluded, or things of those kinds. So that was one of the efforts by Huffman and Close in the early 70s. And in 1973 came an important approach called the pictorial structures by Fischler and Elschlager, which was again reinvented in the early 2000s. I'll talk about that a bit later. But what they talked about there was they wanted that given a visual object's description, that somebody should be able to find out the object in a photograph. So the part of the solution was to define an object as a combination of individual components and the connections between those components. And they proposed a solution which was firstly a specification of a descriptive scheme of an object, as I said, in terms of individual parts and connections between parts. But they also defined a metric on which one could base the decision of goodness of matching or detection based on such a descriptive scheme. This was a significant development at this time, and a lot of the models that were developed in 2000s inherited this approach to the problem. Then between 1971 and 1978, there were a lot of efforts that were attempted by researchers, and that period was also known as the winter of AI. But at that time, many efforts on object recognition using shape understanding, in some sense trying to envision objects as summations of parts. The parts could be cylinders, parts could be different kinds of skeletal parts, was an important effort in that time. So generalized cylinders, skeletons and cylinders were all efforts at that particular time. And importantly, there was also the world's first machine vision course offered by the MIT's AI lab in that time in the 1970s. So I'll talk about the applications later, but in the 1970s, also one of the first products of computer vision was developed, which was optical character recognition, which was developed by Ray Kurzweil, who is considered a visionary for the field of AI, and this was in the 70s again. Then between 1979 to 1982 was again a landmark development for computer vision. David Marr, whose research is followed until today, and in fact the ICCV conference, the International Conference on Computer Visions, actually gives out a prize named after David Marr for landmark achievements in computer vision. So David Marr proposed a pretty important framework in his book called Vision, a computational investigation into the human representation and processing of visual information. Firstly, he established that vision is hierarchical, and he also introduced a framework where low level algorithms that detect edges, curves, corners are then used to feed into a high level understanding of visual data. In particular, his representational framework first had a primal sketch of an image where you have edges, bars, boundaries, etc. Then you have a 2.5D sketch representation where surfaces, information about depth, discontinuities are all pieced together. And finally, a 3D model that is hierarchically organized in terms of surface and volumetric primitives. So, to some extent, you could say that this also resembles how a human brain perceives information, but we'll talk about that a bit later. But this was Mar's representational framework, which led to a lot of research in subsequent years and decades. In the same period, around the 80-81 time, there was also a significant development by Kunihiko Fukushima called the neocognitron, which is actually the precursor of convolutional neural networks the way we see today. I think it was a significant development for the time. And Fukushima introduced a self-organizing artificial network of simple and complex cells to recognize patterns. In fact, you could call this the original ConNet. It also talked about convolutional layers with weight vectors, which are also called filters today. So that was one of the earliest versions of convolutional neural networks, which are used to this day. So that was the initial years, and now we'll talk about some developments in low-level understanding of images, which largely happened in the 80s. So we may not cover all of the methods, but at least some of the important ones as we go forward. So in 1981, there was a very popular method called optical flow, which was developed by Horn and Shunk. And the idea of this method was to understand and estimate the direction and speed of a moving object across two images captured in a time lag. So if an object moved from position A to position B, then what was the velocity of that object across the two images? So flow was formulated as a global energy functional, which was minimized, and the solution was obtained. And this is a method that was extensively used over many decades, especially for video understanding, and I think is still used in certain applications, such as say compression, video compression, or other video understanding applications. In 1986 came the Canny edge detector, which was a significant development for edge detection. John Canny proposed a multi-staged edge detection operator, which is also known as a computational theory of edge detection. It used calculus of variations to find the function that optimizes a given functional. It was a very well-defined principal method, simple to implement, and became very, very popular for edge detection. So it was extensively used for many years to detect edges, probably until to this day in certain industries. In 1987, there was also the recognition by components theory proposed by Wiedemann, which was a bottom-up process to explain object recognition, where the object was constituted in terms of parts which were labeled as geons. Geons simply meant basic three-dimensional shapes such as cylinders, cones, and so on, as you can see in some of these images here, which were assembled to form an object. Again, this was a theory of visual recognition to see if we could recognize objects in terms of their parts. In 1988 came what are known as snakes or active contour models, which helped delineate an object outline from a potentially noisy 2D image. It was widely used in applications like tracking, shape recognition, segmentation, edge detection, so on and so forth. In 1989 was the first version of backpropagation for convolutional neural networks. So it's not necessarily low-level visual understanding, but I think it happened in the 80s, and that's why I'm talking about it here. And it was applied to handwritten digit recognition, as we'll talk about very soon. Other things that happened in the 80s were the development of image pyramids, representation of an image in multiple scales, scale space processing, processing of an image at different scales, wavelets, which was a landmark development at that time, shape from X, which is shape from shading, shape from focus, shape from silhouette, basically try to get shape from various aspects of image formation, variational optimization methods, Markov random fields, all of this were developed in the 1980s. Then came the 1990s, where the community stepped into a higher level of understanding beyond low level artifacts such as edges or corners or so on and so forth. It started with eigen faces for face recognition, which used a variant of eigen decomposition for doing face recognition. This happened in 1991, which was successful for face recognition, at least in constrained settings. There were also computational theories of object detection by Edelman that was proposed in 1997. Then came perceptual grouping and normalized cuts, which was a landmark step for image segmentation methods that came in 1997. Came particle filters and mean shift in 1998. Scale invariant feature transform. We'll talk about some of these methods in detail, which was an important image key point detector and representation method, which was developed in the late 90s, early 2000s. Then Viola-Jones phase detection, again that came in the early 2000s. Conditional random fields, which was an improvement over Markov random fields. Then pictorial structures, the method proposed in 1973 was revisited in 2005 to develop, they came up with an improved statistical approach to be able to estimate the individual parts and the connections between parts, which was called pictorial structures at that time. And they actually showed that that could work in practice and give good performance for image matching. Pascal VOC, which is a data set that's popular to this day, actually started in 2005, and around that time between 2005 to 2007, a lot of methods for scene recognition, panorama recognition, location recognition also grew at that time. Constellation models, which were part-based probabilistic generative models, also grew at that time to be able to again recognize objects in terms of parts and how the parts were put together in the whole. And deformable part models, a very popular approach, I think considered one of the major developments of the first decade of 2000 of the 21st century, came in 2009. And since then, of course, the big developments have been deep learning. So let's briefly review them too. In 2010, the ImageNet dataset was developed, and the purpose of the dataset was that until then, a lot of developments in computer vision relied on lab scale datasets. Of course, Pascal VOC dataset changed this to some extent in 2005 and 2006, but many other developments relied on lab scale datasets that were developed in various labs around the world, and it did not give a standard way to benchmark methods and compare them across a unified platform, across a unified dataset. And that's the purpose ImageNet sought to achieve at that particular time. So 2010 was when ImageNet arrived. And 2012 was a turning point for deep learning, as many of you may be aware. AlexNet won the ImageNet challenge. Until then, all the models that won ImageNet until 2012 were what are known as shallow models. So you extracted some features out of the images and then used machine learning models such as support vector machines to be able to do object recognition. So in 2012, AlexNet came into the picture, and it was the first convolutional neural network that won the ImageNet challenge. And it was a significant achievement because it took the accuracy in the ImageNet challenge by a significant amount beyond the previous year's best performers. We'll talk about the numbers and all of these details when we get to this part in the course. Then in 2013 came a variant of a convolutional neural network called ZFNet, stands for Zeiler and Fergus. It won the ImageNet challenge. Then Also, region CNNs or RCNNs were first developed in 2013 for object detection task, and people also started investing efforts in trying to understand how CNNs work. In 2014, InceptionNet and VGG models arrived. Human pose estimations were developed, so CNN started being used for other tasks beyond just object recognition. Deep generative models such as generative adversarial networks, GANs, and variational autoencoders, VAEs, also were developed in 2014. In 2015, residual networks or ResNets arrived, and CNNs matched human performance on ImageNet. It was again a landmark achievement. 2015 also saw segmentation networks that came into the picture. Fully convolutional networks, SegNet and UNet were all developed in 2015 for the task of semantic segmentation or labeling every pixel in an image with a particular class label. The COCO dataset also started appearing at that time, and also the first visual question answering dataset, VQA dataset, was actually developed in 2015. In 2016, moving beyond region-based CNNs for object detection, single-stage methods such as you only look once and single-shot detector, YOLO and SSD were developed. The Cityscapes dataset arrived. The visual genome dataset arrived, and 2017 was the start of a higher level of abstraction in understanding images, which is scene graph generation. Given an image, how do you understand what is the scene graph? A person sitting on a horse, or a man going on a motorbike, so on and so forth. And in 2018 and 19, higher levels of abstraction, such as the visual common sense reasoning dataset, where we try to see if we not only give an answer to a question on image, but can also give a rationale to that answer. And tasks such as panoptic segmentation have been developed. So as you can see, this journey has focused on going from low-level image understanding to higher and higher abstractions of the world we see around us from images. From an application standpoint, we're not going to walk through every application, but at a high level, in the 1970s, as I already mentioned, one of the earliest products that was developed was optical character recognition by Kurzweil Technologies, by Ray Kurzweil. That was one of the earliest successes of computer vision, you can say. In 1980s, most of the industry developments were in machine vision, which installed cameras in various manufacturing setups or industrial settings, probably finding defects in processing chips, for example, or even in smart cameras, where some of these algorithms like edge detection and so on and so forth were embedded as part of the manufacture of cameras itself, which I think is known as smart cameras, which is, I think, a field that's important even today. In 1990s, slowly the applications of vision started growing. Machine vision in manufacturing environments continued to grow. Biometrics, or recognizing people from images, could be from gait, could be from face, could be from iris, could be from gestures. All of that started growing. Medical imaging started becoming important. Recording devices, video surveillance, all of them started growing in the 90s. In 2000s, more of all of these, better medical imaging, object and face detection, autonomous navigation started in the mid 2000s, Google goggles, vision on social media, all of that started in 2000s. And in 2010s, I'm not even going to try listing the applications. I think it's grown to a point where vision applications are in various domains all around us. Hopefully that gave you a brief perspective of the history of computer vision over the last few decades. I would recommend you to read Selinsky's chapter 1 at this time, and also read some of these links that have been shared as part of these slides. Every slide had a footnote where the information was taken from. So go through some of these slides, go through the links. You'll be able to understand how some of these topics grew in specific areas on those links. We'll stop here for now and continue with the next topic very soon. Here are some references if you'd like to take a look.